Question number 2. Here we go. So it says find f of 3, f prime of 3, double prime of 3, triple prime of 3. So this is really just a question of, do you know how to get a Taylor approximation? Because the Taylor approximation is given to us already. And what we know is that, t of x equals, f of c plus f prime of c x plus f double prime of c x minus c, this should be minus c, over 2 factorial plus f triple prime of c x minus c cubed, and this should have been squared, over 3 factorial. So we know all that. So then we just need to identify that this is a Taylor approximation about x equals 3. We're trying to find these values. So the first one, the easiest one, f of 3 is 5. F prime of 3, well, since there is no something to the x, x to the 1, that's missing here. So we know that f prime of 3 is 0. F double prime of 3, well, we get that 12. To find this out, we know that 12 equals f double prime of 3 over 2. So f double prime of 3 equals 24. And lastly, f triple prime of 3 over 3 factorial equals 4. So f triple prime of 3 equals, multiplying that out, also 24. So is there enough information? So we're done with this. Is there enough information to determine whether there's a critical point at x equals 3? Is it a max or a min? So at 3, there's a critical point because of the wonderful thing she does. Because f prime of 3 equals 0. So when the first derivative equals 0, that's a critical point. So is it a max or a min? Well, because of the second deriv test, we know that it's a min. So a reminder of the second derivative test. Looking at the second derivative, it's 24. So if the second derivative is greater than 0, we know that the function's concave up. And if it's concave up and there's a critical point, then therefore that's it right there. It's the local min. So that's the first 2 questions. Part C, is there enough information to determine whether there's a critical point at x equals 1? Well, while we do have this Taylor approximation, we don't know the actual function. So I don't know anything about f prime of 1 or f double prime of 1. I could approximate these. I could approximate these values by taking the first derivative of my Taylor approximation, but it's not good enough. So because my Taylor approximation is not centered around x equals 1, and because I do not have the function itself, there's not enough information to determine whether there's a critical point. So question D says, if the fourth derivative on 3, 6 is less than or equal to 8, is it possible that f of 6 is negative? Explain. Well, we know that what we could find is an approximation for t of 6, or for f of 6. So I can say f of 6 is roughly t of 6, and t of 6 is 5 plus 12 times 3 squared plus 4 times 3 cubed, and this equals 221. But that's my approximation, and it's likely that f of 6 is going to be close to this. So because this number's so big, is it possible? Is it possible that f of 6 is negative? So if it were negative, that would be an enormous error. So that brings up, oh, error. We need to find error. So we're going to use the our equation to find the error from a Taylor approximation. So we know that the error will equal m over, let's see, n plus 1 factorial times, in this case, 6 minus 3 to the n plus 1. And what is this m value? Well, remember the m value is the maximum that the n plus 1 derivative is on some interval. So in this case, my m value, they tell us, is 8. So it's 8 over, and since we were using a 3-degree polynomial, a third-degree polynomial, so n is 3, so we have 3 plus 1 factorial times 3 to the 4th. So what does this equal? Well, we get 81 over 4 times 6. Sorry, 8 over 4 times 6 times 81. Oh, there's the 81. And so this ends up equaling 27. So that's my error. So what that implies is that the f of 6 is going to equal 221 plus or minus 27. And because this was my t of 6 plus or minus my error. So therefore, f of 6 cannot be negative, because the smallest it would ever be, the smallest f of 6 could be is 221 minus 27, which is nowhere close to negativeness. And that is the answer for question 2.